Hi, I'm Tatsuya Masushima. Today, I present deployment exchange reinforcement learning via model-based offline optimization. Our shows impressive success and promising for complex real-world decision-making. The method usually depends on frequent data collection and updates of the policy. However, in many real-world applications, there are a number of costs with deployments of a new data collection policy, which we want to reduce. Relating to our motivation, recently many offline methods have been proposed and shows a strong performance. In offline RL, agents run from a fixed dataset, and only single deployment is allowed. Often, the agent fails to run from scratch or small datasets. Here, we propose deployment efficiency, which counts how many times the data collection policy has been changed from random policy to solve the task. For example, SEC is around some percent, but about 1 million deployments are needed. On the other hand, offline IR methods such as BCQ and BRAC collect datasets only once, but often fail to run from a random policy. A deployment efficient method stands in the middle, and ideally runs a successful policy from scratch by deploying only a few distinct policies. In order to achieve such deployment efficiency, we found recursively applying this offline RL is not practical. This is because offline RL assumes massive dataset and the sample efficiency is relatively low. So each iteration between deployments needed to work well on much smaller datasets. We believe model-less RL is better suited, which shows high sample efficiency in online RL. In this view, we propose BayLearn, behavior regularized model ensemble, which incorporates model-based methods into offline RL and can also be applied to limited deployment setting. There are two tracks in BayLearn for high sample and deployment efficiency. The former is dynamics model ensemble. In order to prevent policy from exploiting model bias, BayLearn uses an ensemble of multiple dynamics models. Its model is trained with MSE loss of next state prediction. During training of the policy, we randomly select a dynamics model and roll out one step. This procedure is repeated till the termination. The second trick is conservative policy update with behavior regularization. We first approximate the behavior policy from the dataset. We then set the clone policy as the initial policy and optimize the target policy using TRPO-like conservative update. This optimization process works as an implicit scale regularization, which is different from the explicit scale penalties to values in previous offline methods. This trick can manage discrepancy between two dynamics and the run model. As evaluations, we perform experiments in simulator. We firstly evaluate the performance as an offline IL. Using offline locomotion datasets, we try BCQ, BRAC, and BREMEN. The results illustrate BayLearn achieves competitive performance with the state-of-the-art. Next, we assess the sample efficiency. For this purpose, we generate 10 times to 20 times smaller datasets. Surprisingly, we found the performance of BCQ and BRAC can be worse than behavior cloning baselines. On the other hand, BayLearn can improve the policy and achieve highest performance in most conditions. So we can say BayLearn is a stable and sample efficient offline method. We then compared in limited deployment settings where we recursively apply the offline methods. BayLearn, the purple line, achieves remarkable performance with only with 5 to 10 deployments, while previous methods struggle to make any progress. Additionally, we tried more realistic robot manipulation. Only BayLearn shows stable improvement and high performance, while other methods fail to run. These results suggest that model-based methods satisfy both sample and deployment efficiency. This is a result of locomotion. The agent initially performs almost randomly, but learns to run faster only with 5 deployments. This is the result for racing. We can see BayLearn stably improves the performance and runs almost optimal policy with a handful of deployments. We have more detailed paper in archive, Thanks for watching.